So this is Chapter 8, Part 2, Reaction of Alkenes. Part 1 covered all the way up to halohydrin formation. This video will pick up at catalytic hydrogenation of alkenes, which is the addition of H2 in the presence of a catalyst. So there's two classifications of catalysts. We have platinum, palladium, and nickel, and those are said to be heterogeneous catalysts because they are in a different phase than our alkene. So these are often solids, whereas Wilkinson's catalyst is said to be a homogeneous catalyst because it's in the same phase as our alkene. This is going to follow the syn addition. Also, it's important to note that oftentimes we'll see deuterium on our alkene because it's scrambled with hydrogen. Deuterium is just an isotope of hydrogen. This reaction does not require any arrow pushing. Just know that catalytic hydrogenation is the addition of hydrogen in the presence of a catalyst. In this example, we have platinum. Also paying attention to our orientation of addition. It does need to be in the syn addition, so they must be in the same phase. So because our deuterium is wedged, our hydrogen has to be dashed. If our deuterium was dashed, then our hydrogen would have to be wedged. Again, the catalyst could be platinum. We could even have nickel on here. But that is catalytic hydrogenation of alkenes. I will go over the structure of Wilkinson's catalyst just because underneath the arrow, we might write Wilkinson's, or we might draw the actual structure. Just know that it's really big and bulky. We've got 3 big phenyl groups. And then a chlorine. So this right here is what Wilkinson's catalyst looks like. And this is our only homogeneous catalyst that we will use in Organic 2 for catalytic hydrogenation of alkenes. Next, we're going to move to the addition of carbenes. This is a cyclopronation. So we're going to use a carbene and react it with an alkene to create a cyclopropane. Also, this should be a pair of lone pairs, not a negative charge. There are 3 different methods. We could use diazomethane. There's the Simmons-Smith, and then alpha elimination of a haloform. So for the first 2 methods, diazomethane and Simmons-Smith, this is just, again, going to be a cyclopronation where our carbenes are just carbon and hydrogen. However, alpha elimination is going to create a halogenated carbene. So instead of it being 2 hydrogens, it'll be 2 halogens. The first method, diazomethane, it takes place in the presence of UV or heat, but diazomethane itself is very toxic and it's very explosive. It creates way too many side products, and this is just a terrible method to create a cyclopropanation. So this isn't really seen much. However, and that is supposed to be CH2, not CH3. CH2N2. But diazomethane is very toxic, it's explosive, and it creates too many side products. So it's definitely not a great method to use. However, Simmons-Smith, this is the best method for cyclopropanes, it's very stable. It does not create a lot of side reactions. So this requires the Simmons-Smith reagent, which is whenever we have methylene iodide reacting with zinc copper, and it's going to create this right here that we call a carbenoid. So if we had an example such as this right here, this I could recognize as the Simmons-Smith reagent, the carbenoid, and so I know that that's going to create a cyclopropane. The third method is alpha elimination of a haloform. Again, this is going to create a halogenated carbene because over here we just have two hydrogens. So a haloform is dehydrogenated in the presence of a strong base to create a halogenated carbene. So if we had a reaction and our conditions on our arrow was CHCl3, NaOH, and water. This is chloroform right here. And then I see that my sodium hydroxide could break apart into my hydroxy ion. That's a strong base. So I know that this chloroform is going to create a carbene with chlorines attached to it. So this would be my final product. Now, you don't need to know this part, but for me, I like to know why do I need my haloform, my strong base, and my water. So whenever we start off with a haloform, because I use chloroform, I'll use that example. It's going to react with the strong base like sodium or potassium hydroxide. And our strong base is going to abstract our hydrogen, giving our carbon a negative charge. Then we'll have a sodium ion and water as some of our end product. And then because chlorine is such a strong leaving group, one of our chlorines will leave on its own, where we will then have a chlorinated carbene. So that's why we need a haloform, a strong base, and we can see here water as well. But you will not be required to break all of this stuff down. I just like to see that. It is important to note for our methods, all three methods, the cyclopronations do not interfere with the cis and trans stereochemistry of the alkene. So essentially, if we were to have a trans molecule, the molecule would stay trans. So if this was an example that we were looking at. Again, I can recognize this as the Simmons-Smith reagent. Therefore, I know that this is an addition of a carbene. This is a cyclopropanation. So whenever we add our cyclopropane, our stereochemistry does not change. Everything stays the same, which, by the way, we would not have a double bond. We got rid of that after we added our carbene. So those are the three methods. You are not required, again, there's really no arrow pushing. It's just a matter of identifying the reagent and knowing what your carbene will look like. So that is carbene addition. Next, for epoxidation. Epoxidation is going to be the formation of an epoxide in the presence of a peroxy acid. So an epoxide is a three-membered cyclic ether that looks just like this. A peroxy acid is a carboxylic acid. However, it has an extra oxygen atom, and that is what we call the peroxy linkage. So it looks like a carboxylic acid, but we're going to throw in one more oxygen, and this is what we call a peroxy acid. Some examples are peroxybenzoic acid, peroxyacetic acid, or MCPBA, metachloroperoxybenzoic acid. But what you really want to look for is this 3 oxygen linkage right here. In a condensed formula, that's what you would see. 3 oxygens, that should be a dead giveaway. This is a peroxy acid. Now, this is a concerted reaction, and talking about the stereochemistry, very similar to our carbene addition, it is not going to interfere with the cis and trans stereochemistry and geometry. So essentially, the general outline of this reaction is we have an alkene. It reacts with a peroxy acid. Oh, let me draw that out actually. And then it will create an epoxide. We see our 3-membered cyclic ether. And then we'd have some type of carboxylic acid as our side product. Again, this is a concerted reaction. So all of the bonds are forming and breaking all at once. I'll go over an example. However, I don't believe that you will be required to show the entire mechanism. But what I like to do is I like to draw my alkene standing up. And we're going to react with our peroxy acid. So what's going to happen is this oxygen that's bonded to the hydrogen is what's going to form our epoxide. And I need to draw my arrow from the bond between my oxygen and hydrogen to my double bond, and then from my double bond to my oxygen. And so now the bond between my two oxygens right here, this is now going to form a new carbonyl group. And then the bond between my carbonyl group that currently exists is going to create the new oxygen and hydrogen linkage. So whenever we do that, I've generated my epoxide. And then a carboxylic acid. It's a lot of arrow movement, so Again, I wouldn't get too detailed with the mechanism, but just be familiar that whenever you see a peroxy acid, you're generating an epoxide. And some of your side product will have some type of carboxylic acid. Sometimes, whenever we use MCPBA, whenever we use our metachloroperoxybenzoic acid, oftentimes we'll need a solvent to help push the reaction. So we could use something like carbon tetrachloride. And our final product would still be an epoxidized molecule. So that is epoxidation of alkenes. Now we're going to go over dihydroxylation of alkenes. This is going to be the addition of two OH groups. We call these glycols. Di to hydroxy OH, two OH groups. So there's two different ways we could do this. We could do this through the acid catalyzed opening of epoxides, and then we could do this through syn dihydroxylation. So the first method, acid catalyzed opening of epoxides. So once we've created our epoxide, we can actually swing open our ring. And so this ultimately will form an anti-diol because it's going to be the anti-addition. And this is going to happen in the presence of a strong acid like a hydronium ion. And we'll have water acting as our nucleophile. So the first step is, once we have our epoxide, whoopsies. We have to pronate it because our oxygen, it's in a neutral state. So it kind of favors being in that position. It's really not willing to swing open unless if we pronate it, again, using the hydronium ion. And so now our oxygen will be bearing a positive charge. And we have water. The second step is going to be a backside attack of our water on the most substituted carbon. So my water is going to attack this carbon right here. And it's going to cause my ring to swing open. And that is acid catalyzed opening of epoxides. Whenever you do, if you were to see acid catalyzed opening of epoxides on the exam, we'd probably use some wedges and dashes. So that way we can see the stereochemistry. So that way we can see the anti-addition. So I'm going to add that in. So let's say that our methyl group started off wedged. Again, the formation of our epoxide, it does not create or it does not interfere with any stereochemistry. So our methyl group would be wedged and our epoxide would be dashed. And then once we had a backside attack, of our water. We know that if our epoxide is dashed, then our hydrogen down here has to be wedged. And so whenever our ring swings open, this bottom carbon, the stereochemistry does not change. Our hydrogen will be wedged, and our alcohol will be dashed. However, whenever we perform the backside attack of our water molecule, it's going to invert our methyl group. So our methyl group will go from wedged to dashed. And then our water molecule is going to add in the wedged formation. And then, of course, because our oxygen is pronated, then we would have to depronate. So our final product, on the top carbon, we'd have a wedged alcohol. And then on our bottom carbon, we'd have a dashed alcohol. So we can see how that is the anti-addition. So that is one method for dihydroxylation. This follows the anti-addition. The other method we could use is syn dihydroxylation. And with syn dihydroxylation, there's two common reagents we could use. There's osmium tetroxide and then potassium permanganate. So for our osmium tetroxide, we are going to add our osmium tetroxide, and then it's going to hydrolyze in the presence of hydrogen peroxide to form a glycol. Both of these, the reagents, osmium and potassium, it is going to be a syn addition, and it is going to be a concerted reaction. So osmium tetroxide, it's very expensive. It is toxic and very volatile, but it gives really, really, really good yields. So if we were to have this alkene, our osmium tetroxide has osmium in the center, and then it's surrounded by 4 oxygens, all in a neutral state. So it's going to add, our osmium is going to add to our alkene. So we're going to have a double bond to one of our oxygens. The bond between our osmium and our oxygen that we just drew an arrow from will go over here, and then we're going to have an arrow from our osmium to our double bond. This happens all at once, but it creates what we call an osmate ester. Excuse me. So we can see that we've linked our osmium by 2 oxygens. And that is an osmate ester. And then, in the presence of hydrogen peroxide, we're going to hydrolyze to an alcohol, and then to another alcohol. This is a syn addition, so our alcohols both have to be wedged or they both have to be dashed. The other reagent that we can use is potassium permanganate. Potassium permanganate is also going to hydrolyze, but it will be in the presence of water, but it's still going to form a glycol, and it's a syn addition. Now, potassium permanganate can be used for a lot of different reactions, but for syn dihydroxylation, our potassium permanganate must be cold and dilute. This is very, very important. Cold and dilute. And so it's still the same idea. You start off with your alkene. It's going to react with your potassium permanganate. It's surrounded by 3 carbonyls, and then the other oxygen is going to be in a negative state. But we need a bond going from our double bond, or from our permanganate to our double bond from our double bond to one of our oxygens. And then this is kind of the little intermediate that we would be creating. Where we add the entire permanganate compound. And then lastly, it just hydrolyzes in water. So we have an alcohol and then another alcohol. Again, keeping in mind that this is the syn addition, so our alcohols both need to be wedged. They both need to be dashed. We cannot have one wedged or one dashed because then that would be the anti-addition, and this is not anti. So that is syn dihydroxylation and acid catalyzed ring opening of epoxides. Next, we have oxidative cleavage. This also uses 2 different reagents. There's potassium permanganate, and then we also have ozonolysis, which is going to be utilizing ozone, O3. So for potassium permanganate for oxidative cleavage, essentially what we're doing with oxidative cleavage is we're just cleaving double bonds to make aldehydes and ketones. The only difference between potassium permanganate and ozonolysis is some double bonds can be further oxidized. So potassium permanganate must be warm and concentrated. Warm and concentrated. For oxidative cleavage, whenever we're cutting double bonds, warm and concentrated. Whenever we are creating glycols, syn dihydroxylation, our potassium permanganate is cold and dilute. Make sure you know the difference between the two and the conditions of your potassium permanganate for each reaction. So again, oxidative cleavage, we're going to cleave our double bonds to make aldehydes and ketones. With potassium permanganate, our aldehydes are going to further oxidize to carboxylic acids, and then terminal double bonds will oxidize to carbon dioxide and water. So for example, oxidative cleavage, you kind of have to look at it as a puzzle with puzzle pieces. With our warm and concentrated potassium permanganate, It has to be warm and concentrated. So step 1 is we cleave our double bond in half. And so for the left side of our double bond, we have CH3C, CH3, and then for the right side of our double bond, we just have a methyl group and a hydrogen coming off our carbonyl group. So on the left side, we have a ketone. On the right side, we have an aldehyde. Our aldehydes are oxidized to carboxylic acid. So this is how potassium permanganate would cleave. We'll go over a couple of more examples because this can be a little bit more, this can be a little confusing, but just kind of break everything down. This is also why knowing your functional groups is very important. Again, aldehydes are carbonyl groups directly bonded to hydrogens. Alrighty. So we know this is another oxidative cleavage. We're going to cleave our double bond in half. What I like to do is I like to throw any hydrogens around my double bond. So on the left side of my double bond, I won't have any hydrogens. On the right side, I'll have one hydrogen going up. So on the left side of my double bond, I have my cyclohexane and then my carbonyl group. On the right side of my double bond, I have a hydrogen and then 3 carbons, so a propyl group. And so the left side of my double bond, this product is a ketone because my double bond is directly bonded to 2 carbons, whereas over here I have an aldehyde because I can see that my carbonyl group is directly bonded to a hydrogen. So this right here is going to further oxidize into a carboxylic acid. So after you cleave your double bond, just identify what's a ketone, identify if you have an aldehyde, so then you can further determine what needs to be oxidized. So now we're going to look at our 4th point right here, where we talk about terminal double bonds. So let's use this cyclic structure. So now I have 2 double bonds that I need to cleave. I have a double bond that's within this ring, and then I have this terminal double bond right here, right? Because this is just a CH2. So if we're to cleave the inside of our cyclic structure, I like to throw down my hydrogens because I know that once I cleave this, I would be generating 2 aldehydes because of the direct bond of our hydrogens to our double bond, which means that it would further oxidize to a carboxylic acid. So that's going to be what happens whenever we cleave our first double bond. And then with my second double bond, I would have my oxygen right there. And this is a ketone because my carbonyl group is directly bonded to 2 carbons. However, this terminal double bond right here, I'm so sorry, I have a heavy hand today. This terminal double bond, which is going to be the bottom portion of our double bond, is going to further oxidize to carbon dioxide and water. If we were to add another double bond to this ring and cleave it, then we'd have another carbonyl group, and then we'd have 2 moles of carbon dioxide. If I were to add another carbonyl group, another double bond, and it's a terminal double bond, then I would have another mole of carbon dioxide and water. So that's oxidative cleavage using potassium permanganate. Now we're going to go to ozonolysis, where again we are going to cleave double bonds to make aldehydes and ketones. However, there is no further oxidation of our to our carboxylic acids or carbon dioxide or water. However, ozonolysis again uses ozone, O3, and it adds to a double bond to create an ozonide. And then our ozonide is going to be reduced by either zinc or dimethyl sulfide to form our aldehydes and our ketones as our main products. So here's our alkene. And here's our ozone. Our ozone is going to add to our double bond. And this is what we call our ozonide. And once this is created, then it's going to be reduced. Oftentimes you'll see dimethyl sulfide. And I put an ethyl group. And so then what it would do, essentially still we're just going to cleave our double bond in half. I was just showing you what the ozonide looks like, though you really won't be required to draw the structure. Just know that with ozonolysis we create an ozonide. So I see on the left side of my double bond, I have an aldehyde. And on the right side, I've got a ketone. And they just stay as aldehydes and ketones. They will not reduce, they will not oxidize. And that's just going to be your final product. Now we're going to talk about the polymerization of alkenes. So polymers are large molecules composed of small repeating units, and these small repeating units are what we call monomers. There's 3 different methods. There's cationic polymerization, free radical polymerization, and then anionic polymerization. For cationic polymerization, it's going to generate a carbocation intermediate. And then there's 2 different reagents that we could use to initiate our polymerization reaction. We could use either sulfuric acid or boron trifluoride in water. So whenever we use sulfuric acid, let's react with isobutylene. What's going to happen is our double bond is going to be pronated by one of our hydrogens from the sulfuric acid. So in doing so, we have CH3, 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 and now we have our carbocation. This is going to be our isobutylene. This is going to be our monomer. So then we're going to add to our carbocation by using another isobutylene molecule. Showing our arrow from our double bond to our carbocation. And now that we've put 2 monomers together, we call this a dimer. And this occurs over and over and over and over and over again until we terminate our growing chain by the loss of a proton. So let's say that our chain got really, really, really long. I'm just going to fill in the space real quick. Okay. Because we use sulfuric acid to initiate our reaction, our sulfuric acid can also terminate our chain. So we'd abstract a hydrogen, the bond between our carbon and hydrogen will fold to satisfy our carbocation. So then we'd have all these repeating units over here. And then we'd create a double bond, putting our carbon back into a neutral state. And that is cationic polymerization. Again, boron trifluoride, BF3 in water. That is another initiator for cationic polymerization reaction. Except for it will initiate the reaction a little bit differently. Our boron trifluoride is going to react with water. We're going to add the entire water molecule. And then because our oxygen is pronated, if we were to use our isobutylene again, what would happen is our double bond would come abstract one of these hydrogens, and now we'd have three groups or three hydrogens attached to our carbon. And then now we have our first monomer, and then it's going to react over and over and over again with isobutylene. The mechanism on how the polymerization reaction initiates, it's important, but more than anything, just focus on the conditions of the reaction, that we're generating a carbocation intermediate, and that sulfuric acid and boron trifluoride can initiate the reaction. And just know that polymers are large molecules composed of small repeating units. For free radical polymerization, we'll have a radical intermediate, and because we're talking about radicals, now we're going to need a peroxide to initiate our reaction. So after we go through the homolytic breakage and cleavage, then our radical can initiate a polymerization reaction using half arrows. This front arrow is going to generate our alkyl radical intermediate, and then this will repeat over and over and over again using our half arrows until the reaction is terminated. Lastly, we have anionic polymerization. This is going to have a carbon ion intermediate. This is pretty rare. You won't see this as much. But anionic polymerization reactions require strong electron withdrawing groups to initiate the reaction, and it's because they really help stabilize the double bond. So for example, if this were to react with isobutylene again. Then we'd add our strong electron withdrawing group to our chain, and one of our bonds from our double bond is going to turn into a lone pair on our carbon, generating our carbon ion intermediate. So that's polymerization. Remember the three methods: cationic, generating a carbocation intermediate, and it utilizes two reagents like sulfuric acid and boron trifluoride. Free radical polymerization, it requires a peroxide, and it has an alkyl radical intermediate. Anionic polymerization is rare, but it has a carbon ion intermediate, and it requires a strong electron withdrawing group to initiate the polymerization reaction. So our last reaction that we're going to go over is olefin metathesis. So olefin metathesis is a little bit different. The goal of olefin metathesis is to rearrange our alkylidene groups. So this is Greek, actually, if we break it down, metathesis. Meta means change, and then thesis is position. So this reaction really just serves to trade and interchange our alkylidene groups. There are two catalysts that we could use. There's Schrock and then there's Grubbs. So both of these catalysts have a metal atom, and metal is signified by M in brackets, and it's double bonded to an alkylidene group. Alkylidene groups are just double bonds, CH, and then some type of alkyl group. So both Schrock and Grubbs have catalysts that look somewhat like this. There's three different methods for olefin metathesis. There's cross metathesis, ring closing, and then ring opening polymerization. But essentially, the main idea is say we have alkene A and alkene B. Essentially, what we would do is we would cleave our double bond in half, and we can see our alkylidene groups. And then whenever we were to apply either Schrock or Grubbs, one of our catalysts, the idea is that we could kind of just pick up different ends from each molecule and stick them together kind of how we want. So we could have the left side of alkene B, and then the right side of alkene A. They could be in the trans position. It's very general, kind of very vague, which is why I'm glad there's not really any arrow pushing with this mechanism, with this reaction, because it's kind of a little funky. But what should really be a standout with olefin metathesis is definitely your catalyst, Schrock and Grubbs. For cross metathesis, that's an example that I should have kept that up there. Cross metathesis, let's say we're to have alkyl groups. We apply our catalyst, and then we could have our trans and our cis products. We also have ring closing metathesis. So I'm going to have to draw a heptagon, so bear with me. Okay. So if we were to react this structure with the catalyst, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And essentially, what Schrock and Grubbs can do is they can close the ring and now we have 1, 2, 3, 4, 5, 6, 7 carbons plus our 2 other carbons. So our final product still equates to 9. We just closed our ring. We also have ring opening polymerization. So we could start with a bicyclic compound in this example. And if we were to add one of our Schrock or Grubbs catalysts, essentially this ring would open up. And then it would polymerize over and over and over again. And so this right here would be our monomer. And then it would just repeat and repeat and repeat until the chain gets terminated. So that will conclude Chapter 8, Part 2, Reaction of Alkenes. For the latter part of this video, or just the latter part of Chapter 8, just in general, it's not very heavy on the mechanisms, but more so understanding the concepts, the reaction conditions, knowing that we could use multiple reagents for dihydroxylation like potassium permanganate and osmium tetroxide. But potassium permanganate needs to be cold and dilute for dihydroxylation because whenever it's warm and concentrated, we use it for oxidative cleavage. So the latter part of Chapter 8 isn't too bad, just really, really narrow and hammer down on those reaction conditions. So if y'all have any questions, please feel free to reach out to me.